screen sharing, can you enable it? Yeah, thank you. Right. Yeah, good morning, members. Nice to see you all. So today the class would be on just a second. Microsoft Whiteboard. Yeah. So we will discuss the topic concept work concept of work. So work done by a force. So this is a very important concept, not just in mechanics, but the entire physics. Because once this is introduced, in every chapter you will see questions involving work calculation and how mechanical energy can be transferred from one body to other body with the effect of work done by a force. So this is something that is very, very important concept. So for today, I want to discuss about this. So first thing is about Newton's laws of motion, NLM, if you consider. What Newton says is that with all the observations and analysis, see, you give me any system. It is a systemic approach. You give me a system. First, I'll define the system. Then you go for drawing the free body diagram. Free body diagram. Once you draw the free body diagram, you will understand the forces acting on the system. Ignore the internal forces, just focus on the external forces. So once you know the forces, and you also got some basic understanding of how it is moving, you start writing the equations. Equations of force, net force is equal to mass into acceleration. So you write it along x-axis, along y-axis, along z-axis, and you also take different systems, multiple systems you take until you get enough number of equations. Suppose if the equations are not enough, even after exhaustively using Newton's laws, then you go for additional equations by using constraint equations, constraint motion. Constraints, you will have it. So you have wedge constraint, you have a string constraint, and so on. So use constraints to get additional equations. Once I have sufficient number of equations, you make sure that number of equations equals to number of unknowns. So number of equations equal to number of unknowns. Then you have it. You solve them. Solve for accelerations and unknown forces. Some of the forces could be unknown. So this is a method given by Newton. This is a standard method of solving any question using mechanics. Theoretically speaking, every problem in mechanics can be solved using this method. If it is solvable, then you have this method. There is nothing great about it. Simply, boringly, you follow this procedure over and over again, and then you'll be able to solve the accelerations and unknown forces. But suppose in some situations you don't want acceleration, but you want velocities. You want to find velocity, you want to find position, and you want to find the path. Okay, if these are the things that you want to find, then you need to use mathematics, additional mathematics. That's where calculus comes in. So what he says is that you have the cause-effect relation. Okay. Acceleration now affects the velocity later. So we'll write like this: velocity at t plus dt, velocity at t plus dt equals to velocity at t. And then you have that extra velocity that is coming because of acceleration. Acceleration at t times dt. This is the equation of kinematics. V final minus V initial equal to acceleration to time duration. Same way you can go for position vector. Position vector at t plus dt equals to position vector at t. Position vector at t. And then velocity at t plus dt at t dt. So this is where you get calculus. And then you got to do integrations and so on. You can keep repeating it. Keep on repeating it. Now that you got velocity at t plus dt, you can find velocity at t plus 2 dt, at t plus 3 dt, and so on. This goes like a sequence, a series. Suppose you want to find velocity at t plus dt, 2 dt, for example. You go on ahead further. That is velocity at t plus dt plus acceleration at t plus dt, acceleration at t plus dt times dt multiplied by dt. In the same manner, go for position vector. Once you have position vector, you can find path also. Same way, r bar at t plus dt you want, and that is equal to r bar at t plus, this is 2 dt I'm taking, right? R bar at t plus dt, and then v bar, I think system is hanging a little bit. Okay, v bar at t plus dt times dt, and so on. Or otherwise you do integration. Simply you write, this is a sequence you have. At t plus 3 dt you can calculate as e plus 4 dt, t plus n dt, and so on. Otherwise, in general, we'll write like this. In a finite form, v final minus v initial equals to integral a bar dt from initial to final, or otherwise r final minus r initial, and that is equal to integral v bar dt, and all that you get it from initial to final. These are all definite integrations. Remember, in physics, most of the times we get definite integrations. So this is all general procedure. Using Newton's law, you find acceleration, integrate acceleration to find velocity, integrate velocity to find displacement, and so on, or position vector. So with that, Newton says that you give me any question, I can solve it. If it is solvable, this is the method. You give me, I'll solve it. With that, we have initial chapters in mechanics. You have Newton's laws, friction, and then you'll study about constraint equations, circular motion, and by that time you will be able to solve any problem given this. Now the problem arises about the mathematical complexity. Now that physics ideas are over, you can solve any question using this method. Now comes mathematical complexity, especially when the particle is going in a two-dimensional motion, three-dimensional motion, complicated path and complicated forces are acting, acceleration is varying direction, magnitude and so on. When you want to do this, then sometimes integration methods would be so complex. Probably we'll have to use computer. They use computers to solve these equations because humanly it is impossible to solve them. And some of them are so complicated that it's not worth spending that much of time to solve that kind of things. So that's where the alternate method comes. Now that Newton has given the method, it is ideally there to solve any kind of problem. But in some situations where the motion is very, very complex, this method can be very, very lengthy, time consuming. In such situation, we would like to have an alternative method. So that's how this work energy theorem has to be introduced. Work energy theorem. So this work energy theorem is introduced only to simplify things, only to give an alternative method to find velocities. It's not a new theory as such. The reason behind work energy theorem also, the student should understand that. Simply don't start a new chapter. Why are we studying? Because sometimes Newton's law can be very complex. That's why we are looking for an alternative way of solving a question, especially when you are concerned about speed, not velocity. When you are not worried about in which direction it is traveling and you want to find the speed, this particular method can be very effective in solving a question. It gives an alternative method. So what it says is that, okay, you have F net is equal to mass into acceleration. Mass into acceleration. Sorry. So this is a little lagging part. Mass into acceleration. This you can write as mass into dv bar by dt. This is for the particle, you know it. But this dv bar by dt can be written as dv bar by dl into dl bar by dt. Okay. So if I write that, this becomes dv bar by dl into dot product. dl bar by dt is nothing but velocity. So I think you know it anyway. So you can take that dl the other side, then you will have f net dot dl bar equals to mass into dv bar by dt dot dl bar. So this you can write as m into dv bar dot v bar. dl bar by dt can be written as v bar. All right. And then we integrate either side, integral f net dt dot dl, sorry. That is equal to m into integral v bar dot dv bar. So this is a method we have. You start from initial to final. So this becomes m into v dv is basically v square by 2 So you have V final square minus V initial square. This is what we have the method. V final square minus V initial square whole divided by 2, and that is half mv final square minus half mv initial square. So ke final minus ke initial, you get it. Now this particular relation is actually very important, basic only, but then it is very important because you should know the purpose of it. Why are we doing it? Purpose is to bring a alternative method to Newton's law. To get alternative method to Newton's laws of motion. Whenever you see that Newton's laws of motion is becoming complicated method, then you go for it. This is the purpose of it. But more importantly, it gives definitions. It defines two quantities. It defines work as integral f bar dot dl bar, okay, from initial to final. And it also defines kinetic energy. That is half mv square. So this is a basic idea of work energy. So this work can be used to calculate some complicated forces. You don't have to worry about acceleration. Directly you do the dot product. Most of the times what happens is centripetal forces will not perform any work. So you can avoid centripetal forces. Only tangential forces will be working because only that component of force along dl bar we are considering, which is along the path. So this work energy theorem eliminates, this particular one eliminates all those forces, eliminates the effect of all the forces which are perpendicular to path. Perpendicular to paths. So that is one thing, one advantage with this method. You don't have to worry about the forces which are perpendicular to path. Only that force which is along the path we need to worry, because that dot product we are including, right? That way some forces need not be considered. Even though path can be so complicated, path will get turned because of the forces perpendicular to path. And now that I'm taking up that perpendicular forces, so it becomes simplified. This is a basic idea. Now we'll take some questions on how it can be used to simplify. Now that little bit of theory has been given, but I really want you to appreciate why this method has come. Why to study work done? What is the purpose of defining work? What is the purpose of defining kinetic energy? And then of course later on this concept of mechanical energy comes in, and then you have other forms of energy, electrical, thermal energy, mechanical, chemical energy, electromagnetic energy. All those things will come later. First force, which is considered to be absolute. Handling force is becoming so lengthy sometimes. That's why we packaged it into integral form. We call it as work done. And from work, we also define kinetic energy. Sometimes forces can be so easy to study that I don't have to worry about integration. I can take them as a state function. That's where potential energy comes. Potential energy is there, kinetic energy is there. We combine them together as mechanical energy. So this particular chapter is very, very important conceptually also. All right. Now that we had given the basic introduction to this particular idea, now let's solve some questions. Let me take a question here. So, yeah, take this question. So we have, there's a block of mass m, 4 kg, let us say, which is connected to a spring. And it is kept on a horizontal surface, smooth surface. Friction is not there. So coefficient of friction is 0. And it is pulled. It is given some velocity. The block is given a velocity. Initial velocity of the block is, let's say, 1 meter per second. And then this free end is pulled in this direction with a velocity v0, which is equal to 2 meter per second. So what they are saying is, spring block system lies on a smooth horizontal surface. The free end of the spring is being pulled towards right with a constant speed. So this is taken as constant. So you are holding that free end and then pulling with a constant speed like that. And the block is given 1 meter per second. So this is instantaneous. This 1 meter per second is just instantaneous. So at t equal to 0. That means this velocity of the block is variable, whereas velocity of this free end is fixed. Block velocity can change. Now what is it saying? Spring constant is given K equal to 100 Newton per centimeter. 100 Newton per centimeter. Now the question is, find the maximum extensions of the spring. Find maximum extension of spring here. Find E max. So those who are trying to do, you can just pause the video here and then start solving it. So usually what I see that some aspiring teachers, they think that some high-fi complicated questions they have to solve to become advanced teachers. But if you look at advanced papers, right, they don't give very complicated problems. They give conceptual problems. Multiple concepts they'll give. Each option is one particular concept. It can be exhaustive. But if you focus on concept rather than complexity, I think it will be a better idea to become really good at physics. The advantage with physics is that once you get it, you will not forget. But in other subjects like in chemistry or mathematics, chemistry especially, you learn now, maybe after a while you forget because it's mostly memory based. And mathematics also, if you are not in touch, if you are not solving questions of late, your ideas may not strike that much. But thankfully in physics, you don't have that kind of problem. If you have clarity in concept, the preparation is not needed. Just go there and then you start solving. You will get the ideas automatically. Class will also go very systematically that way. So here, velocity of the block can change, whereas the free end velocity is constant. See, generally what happens is, first thing, whenever you are looking at this kind of questions, first thing that you need to see is that too many things moving, we don't like. We want to simplify it. Free end is also moving, block is also moving. Free end is going with constant velocity, all right. But the block is going with a complicated velocity, variable velocity. Right now it is 1 meter per second, but after that it is going to change. It is going to decrease. So when you have too many things moving, we don't like it. To simplify it, we might want to see if I can change the reference frame. Change of reference. Change of frame. So that would be the first thing that we would like to do. But then when you change the frame of reference, again, I need to deal with pseudo forces. But that pseudo forces will come only when I have non-inertial frames, right? Preferably, I would like to see if there is any inertial frame. Inertial frame meaning the one which goes with a constant velocity. Luckily here, this free end is going with constant velocity. So I can take free end. That's advantage here. Free end I can take because it is an inertial frame. So whenever I'm dealing with inertial frame, problem is much simpler because no pseudo forces involved, and problem becomes definitely easy when you go for change of reference. So the moment you go for change of reference at t equal to 0, if you observe, block is here, all right, and then you got the spring. Now this free end has become fixed. Okay, this free end is not moving. So this is with respect to free end. Okay, Everything I'm observing with respect to free end. Now, in that case, the block will have a velocity. In ground frame, it is already having 1 meter per second. And this free end velocity is reversed and then added to it. You will get 3 meter per second. And that is a velocity at t equal to 0. Okay. Now, what is he asking? Maximum extension he is asking. So the moment they ask you to find maximum extension, you see that only the block will be moving. Block will be oscillating here. It is going to go in simple harmonic motion because one end is fixed now. In this frame, the motion is very simple. Only the block is moving with initial velocity 3 meter per second. Back and forth, it is moving. So you will have E maximum and it goes to an extreme position. Extreme position. So extreme position, when you have, you know that at that moment, velocity of the block in this frame has to be 0. It comes to rest. When velocity of the block is 0, then kinetic energy of the block has to be 0. All right. Kinetic energy of the block has to be 0 there. So now if you look at the forces acting on the body, you have normal reaction, you have mg, you have spring force. But normal reaction is perpendicular to velocity all the times. And mg is also perpendicular to velocity all the times. They don't perform any work. Forget about them. You don't have to worry about the work. That's advantage with work energy theorem. You don't have to worry about the forces which are perpendicular to velocity. They don't perform any work. Only those forces which are along the velocity line, maybe in the direction of velocity or opposite to the direction of velocity. Only such forces you need to focus on. Okay, so the spring force is doing work. Work done by spring force, we need to calculate. I want to use work energy theorem, work energy theorem. WET, I write as work energy theorem. So here work done by gravity plus work done by normal reaction plus work done by spring force equals to change in kinetic energy. All right. So I'll write it from t equal to 0 to extreme position. Work done by gravity is 0. Work done by normal reaction 0. Work done by the spring is half k into initial deformation square minus final deformation square. And that is equal to change in kinetic energy. That is half m into initial velocity, final velocity square minus initial velocity square. So you need to solve it. Half will cancel off. Anyway, here initial deformation is 0. Final deformation, that is Emax, maximum deformation. Initial velocity is known to you, 3 meter per second. And at extreme position, final velocity would be 0. You can use this to solve it. So that part you can look at it. Okay, I used work energy theorem here. Of course, there is another method also. This is one method, definitely. Using work energy theorem is one method. But of course, you can also use conservation of mechanical energy here. Conservation of mechanical energy. I'll write it as COME, conservation of mechanical energy. Now that only spring force is acting here, doing work, spring force is a conservative force. So whenever you are dealing with conservative forces, it is very advantageous. All right, because we can define potential energy for them. Potential energy can be defined as half k x square. In that case, initial energy equal to final energy. We can write that initial kinetic energy plus initial potential energy equals to final kinetic energy plus final potential energy. So this is another way of doing it. Initial kinetic energy, you know it. Initial velocity is 3 meters per second. Mass is 4 kg, they had given. Initial potential energy is 0 because deformation is 0. Final kinetic energy is 0. Final potential energy you have to calculate. Meaning here initial potential energy is 0. Right? This is 0. And final kinetic energy is also 0. Meaning whatever initial kinetic energy is there, that has been converted into final potential energy. There is a transformation of energy from one form to the other form. All right. Transformation of energy, you have it. That anyway, you can solve it. I think you got the idea. Because the moment you are able to change the reference frame, this particular problem becomes very easy. Okay, another example let us consider. Okay, another example. A two-block system I'm considering. And in this two-block system, there is a friction also between the blocks. Example 2. Two blocks are there. Mass M1 and M2. And it is kept on a smooth horizontal surface. This is a smooth surface. Coefficient of friction is 0. And then we are applying a force on M2. And they are moving together. They are moving together. Then we need to find work done by friction between them. Work done by friction on M1. Similarly, work done by friction on M2. These two questions we have to solve. So it is assumed that initial velocity is 0. Okay. And we are calculating, we are observing from t equal to 0 to t time. During this observation period, we have to find the work done by friction on M1 and also work done by friction on M2. So this particular question is simple only, but then it gives you one concept, the physical visualization of what is work done, right? That's why I have taken this question. So the first thing is, you find that you know that friction will be static friction here. The static friction is actually very easy to calculate. It will be F2 into M1 by F1, M1 plus M2. That will be the friction. It's very easy to calculate. So when we discuss about static friction, I'll give you how to give this formula. Directly you can write it. By just looking at it, you can write it. That's a static friction. How do you do it? First find the acceleration. F2 by M1 plus M2 will be the acceleration because they're going together. In order to get the same acceleration for M1, you apply Newton's law, you'll get static friction. So now if you draw the free body diagram, I'll go with the black color only. That seems to be better. So if you draw the free body diagram for M1, only M1 if you see, vertical forces are there, but anyway, they are not going to change the movement of it. It is accelerating horizontally towards right. That means this particular body should experience static friction towards right. So friction is not opposing the motion. Friction is opposing the slip. So this is M2. You have F2 anyway, which is pulled, but this guy is a rich guy. Rich guy would be slowed down by the friction. So it's like a what do you call? In olden days, there are a lot of movies where a rich guy is supposed to be hit and you give it to poor guy. M1 wants to stay there, but M2 wants to go with a higher velocity. The one which tends to get more acceleration are rich guys here. The M2 has to be slowed down. M1 has to be speeded up so that they can go together. Now on the M1, it is positive, force is in the direction of acceleration. Now if you write work done by friction, static friction on M1, and that is simply static friction times displacement of it, positive. And that is equal to F2 M1 by M1 plus M2. And that is equal to into S. S is a half A T square. A is how much? F2 by M1 plus M2 would be the acceleration, because they are going together. Total force by total mass will be the acceleration. So you can simply write that F2 by M1 plus M2, that is acceleration times T square. So this is the work done. Positive you will get. And work done by friction on M2, if you calculate, work done by friction on M2, if you calculate, you will see that it will be negative. It will be minus Fs into displacement. Displacement is half AT square because initial velocity is 0. So M1 is gaining kinetic energy because of static friction, because it's doing positive work. No? Whenever positive work is done, kinetic energy is increased. Whenever negative work is done, kinetic energy is decreased. So what is happening is there is a flow of energy here from M1 to M2. M2 to M1. So you have the situation you can visualize like this. I'll be very happy if you can explain this to the student rather than simply solving a problem. So F2 you look at here. F2 is doing a positive work on M2. That means it is supplying energy to the body M2. So the force is supplying energy. So there is a energy supplied here, E2. F2 is supplying energy to M2 because it is doing positive work. But on M2, if you look at the friction, where is it? On M2, the friction here is technology is doing negative work. Static friction will be doing negative work. Whenever it is doing negative work, it is going to extract energy from the block. So it is taking out the energy from the block. So E1. Now on M1, if you look at it, on M1 friction is doing positive work. What does it mean? It is taking that energy. Whatever energy has been supplied by, whatever energy is being extracted by friction from M2, that has been given to M1. So M1 is gaining energy. M2 is losing energy because of friction. Now you see, F2 is supplying energy to M2. M2 is supplying energy to M1 because of the friction between them. So the internal forces, you see that friction is the internal force here. If you look at the friction, the static friction here and this static friction here. So internal forces, static friction is internal force between them. Internal forces, whenever they perform work, they cause exchange of energy between the bodies. Energy is flowing from M2 to M1. All right. So internal forces cause exchange of mechanical energy. So whenever they perform work, So for example, here F2 is giving some energy. Let's say 100 joules is given to M2. Out of that M2, 100 joules, this friction is taking some 60 joules and it is given to M1. So whenever a force does negative work, it means it is extracting energy. Whenever a force is doing positive work, it is injecting energy. F1 is extracting energy from M2, it's a static friction, and then the same energy has been injected into M1. So that is one physical visualization you need to have, and a student should have that very firmly. So work done basically is a flow of mechanical energy. Flow of mechanical energy. So work meaning flow of mechanical energy. Positive work meaning positive flow. Positive work meaning inflow of mechanical energy. Work done on the body is greater than 0, which means it is inflow of mechanical energy. So work done is negative meaning it is outflow of mechanical energy. The body is losing energy. So I tell them, you imagine force to be a syringe sucking blood from the body whenever the force is doing negative work, injecting some medicine into the body whenever it is doing positive work, like that. That way you can visualize. And whenever internal forces are performing work, they cause exchange of energy. One part of the body, one part of the system loses energy, and the other part of the system gains energy. And there are types of internal forces also. So whenever work done by action plus work done by reaction is 0. Like in this particular case, you see work done by friction on M1 and work done by friction on M2, if you sum it up, it is 0. Whenever work done by friction plus work done by reaction is 0, work done by action plus work done by reaction is 0, which means that there is no loss of mechanical energy as a whole. So whatever energy lost by this guy is completely given to the other guy, meaning there is no permanent loss of energy, just an exchange. So no permanent loss. A permanent loss, there is a technical word in physics which is called dissipation. No dissipation. No dissipation here, simply exchange of energy. And whenever work done by action plus work done by reaction is less than 0, okay, that is the case when you deal with kinetic friction. Kinetic friction does positive work on one body, negative work on another body. Negative work will have more magnitude than positive work. So work done by action plus work done by reaction, when you add it up, you will get negative value for a kinetic friction, internal kinetic friction. That means there is a loss of energy permanently. That means it takes, let's say, 100 joules from M2 and it gives only 80 joules to M1, meaning that some 20 joules of mechanical energy is lost. Then we say that there is a dissipation of energy. Right? The forces which involved there are called dissipative forces. Dissipation meaning permanent loss. It is not temporary loss. There is no retrieval back again. Gone meaning gone forever. And some forces are there which are very interesting. Work done by action plus work done by reaction. Some internal forces. Net is positive. For example, our muscular forces. All right. Or otherwise electromotive force, which produces mechanical energy. So mechanical energy is created, right? Created at the expense of some other form of energy, maybe chemical energy or biological energy, whatever it is. So such forces are called motive forces. Work done by action plus work done by reaction is 0. Such internal forces are called motive forces. Electromotive force or otherwise muscular forces. Example. So where what is happening is chemical energy is converted into mechanical energy, or some other form of energy is converted into mechanical energy. But work done by action plus work done by reaction, this is an example here. You deal with static friction. Static friction is a non-dissipative force. Whereas this is an example of kinetic friction. Kinetic friction causes dissipation. And this one is an example of muscular forces or electromotive force. Okay. So these forces are called muscular forces. Either way, it is observed that whether the dissipative force or motive force, dissipative force cause loss of mechanical energy, whereas motive forces cause gain of mechanical energy. Either way, it is observed that work done would be path dependent in these two cases. These forces are called non-conservative forces. These are non-conservative forces. But this no dissipative forces, some of them are conservative, some of them are not necessarily conservative. That depends. Some of them actually do work, some of them don't do work, but that's a different thing that we will discuss in some other time. So whenever you are studying work, you can visualize it as a flow of energy. All right, work is a flow of mechanical energy. That's a very important one. When you go to thermodynamics, for example, we write work plus heat equal to delta E and all that. Work is a flow of mechanical energy. Heat is a flow of thermal energy. The flow of mechanical energy, flow of thermal energy together will give you flow of total energy supplied to the system, which changes the internal energy. Okay, so that is one example. I'll take one more case. Another example I'll consider. Let's say you have a block M, mass M, and then there's a spring connected to it. I just want to take spring force because spring force is a variable force. So dealing with variable forces are generally difficult. So suppose we want to solve it. Let's say we have a force here, F2, and force here, F1. Initially, it is at natural length. Initially, natural length. Both the blocks were at rest. Let's write M1, M2, so that it becomes a bit lengthy. And the floor is assumed to be smooth floor, and we want to find the maximum extension. Find maximum extension. It's a standard question. You can solve it. It is there in HC Verma also, in any standard book it is there. But I wanted to take it to explain about how to handle non-inertial frames of reference, right? Just for that particular purpose. Now you see M1 and M2 together is a system along with the spring, but this system is not a rigid system. All right, it's a non-rigid system because the separation between the bodies M1 and M2 is changing. So such kind of things, whenever you're dealing with where two bodies are moving in different directions, the immediate idea has to be to use change of reference frame. Okay, that's something that comes naturally. Students and teachers should get that idea very quickly. We need to solve it by using change of reference frame. First, you find acceleration of center of mass. Acceleration of center of mass, let us calculate. And that's going to be F2 minus F1 whole divided by M1 plus M2. I'm assuming F2 is bigger than F1. This is the acceleration of center of mass, which is a constant. All right, which is a constant. So I want to solve it with respect to center of mass. With respect to center of mass. So with respect to ground, if you observe, M1 will go with some M1 V1. M1 will have velocity V1. M2 will have velocity V2. Spring is massless anyway. And center of mass will have a velocity cm. I'm assuming it to the right side because F2 is assumed to be constant. So the same thing we can study as with respect to center of mass. If you look at M1 and then M2, and center of mass is somewhere here, which is fixed. With respect to center of mass is stationary. So velocity of M1 would be V1 cm. Velocity of M2 would be V2 cm. They go up back and forth. They'll oscillate like this. Each block would be oscillating back and forth. It will go up back and forth like this. This also oscillates like this. Both of them undergo simple harmonic motion. So center of mass is stationary and they are going like this back and forth. Simple harmonically they'll be moving. So that way motion became easy. And with respect to ground equal to with respect to center of mass plus center of mass velocity. So motion of center of mass. So you imagine that M1 and M2 already having VCM. Both of them are going together with VCM. Or maybe you can keep a box there. Take a box and place there and the entire thing is going with VCM velocity. So that is translation of center of mass. That does not change the deformation because only because of VCM, there is no change in separation. Separation doesn't change, meaning deformation doesn't change. So that part you can keep it aside. You focus on only that component of velocity which is causing separation here, change of separation. So this is called principle of superposition. Total velocity can be visualized as only VCM plus velocity of each particle with respect to center of mass. This is a motion which is causing change of separation. This is what I want to focus on. This motion does not cause change of separation. That I am not going to consider right now. Leave that. We'll focus only with respect to center of mass. But the problem here was center of mass is a inertial frame. Center of mass is a inertial frame. Sorry, center of mass is a non-inertial frame. Non-inertial frame. Because it is accelerating. No? Non-inertial frame. But advantage is that acceleration of center of mass is constant. So finding the pseudo force is not a very big deal. Just a mass of the each body observed into acceleration of center of mass in reverse direction. Now, with respect to center of mass, if you observe, in addition to F1 is already there. In addition to F1, you will have extra force, pseudo force. Pseudo force will be mass of the observed body into acceleration of center of mass. Same way, if you look at M2 is already experiencing F2 force. In addition to F2, it is experiencing pseudo force, which is opposite to acceleration of center of mass, M2 into ACM. Now, this is F1. No? You calculate these two together, sum it up. And then you sum it up, the sum of these two also. It's actually very easy. Any one of them you calculate, the other one also would be of same magnitude. Because with respect to center of mass, net force has to be 0, including pseudo force. Center of mass is not moving. No? So just calculate F1 and M1 into ACM. F1 plus M1 into ACM is F2 minus F1 divided by M1 plus M2. It's a very standard result you will get. So simplified, you do LCM, F1, M1 you will get but here minus F1 M1 will be there. That will cancel out. F1 M2 will be present, and then plus F1 M2. That's a very standard result. It comes so repeatedly that it's better to remember it, like F1 M2 plus F2 M1 by M1 plus M2. That is going to be the resultant of those two. Let us call it as F star. Even these two together also, if you add, you will get the same thing, because net has to be 0 only. I'm just leaving that to you. So essentially, it is equal to M1 experiencing a force F star, including pseudo force, and M2 also experiencing a force F star, including pseudo force, where F star equal to F1 M2 plus F2 M1 divided by, I think I had written it, same thing, F2 and M1. All right. So this is what I have. Now we need to find maximum elongation. To find maximum elongation, we can use work-energy theorem. So right now velocity is 0. Initial velocity is 0. Even for this also, initial velocity is 0. When it goes to extreme position, the block goes to here, let us say, and this block goes to here. Extreme position. That's also the situation where velocity would be 0. Again, V final is also 0. All right. So this block has moved x1 distance, and this block has moved x2 distance. x1 plus x2 equal to Emax, maximum deformation. So now if I use work-energy theorem, including pseudo force, what do I get? F star into x1 positive. F star into x1 is positive. Yes, F star into x2. That is also positive only. Force and displacement, same direction. What you get is F star into x1 plus x2, which is Emax. All right. So what is the initial kinetic energy? 0. Final kinetic energy is also 0. So this is a energy supplied by F star. This should be equal to energy supplied, mechanical energy, change in mechanical energy, which is equal to change in potential energy plus change in kinetic energy. Change in kinetic energy is 0, because initially is at rest, finally also at rest. Only potential energy has been changed. Kinetic energy, this is 0. So F star into Emax equals to change in potential energy. Change in potential energy is half K into Emax square. So Emax 1 cancels out, and you got two times of F star divided by K. 2F star by K, that will be Emax. In fact, I remember it as a formula type result. A result which is very, very useful. Many times it will be used. 2F star by K, that will be the maximum deformation here. So in this case, we have to change the reference frame, but the reference frame was non-inertial, though force was easy to calculate, pseudo force. That's one. When you look at the first question where the free end was moving with a constant velocity, I changed the reference frame, but there I did not use pseudo force because it was a inertial frame. So likewise, we can do many questions. This is a point I wanted to discuss about for today. Maybe we'll close it here for this particular session. I hope this is useful for you. So what I suggest for the aspiring teachers who would like to grow up faster, see, you focus on concept. getting that feel of it, why we are doing it. Simply solving some high-fi level tough questions, that's not what is required for advanced examination. Understanding, appreciating why we are doing, and a conceptual way, if you do it, definitely you'll be able to do much better and quickly we can learn things. Advantage with physics is that once you are learning them, that's all. You don't have to worry about them. They are there in your long-term memory. So you make use of this particular service. It's a very good platform. And I'm really very happy for the utility of this particular platform, because this particular kind of support is not there anywhere. And Mr. Kiran is really doing a good job. I hope everybody will make use of this particular platform, because there are very good, extraordinary teachers that are going to be joining here to make your learning very rich. Only problem is that you got to wake up early in the morning at 5 o'clock every day. If you can do that and do that consistently for 8 months, whatever has been stipulated here, you will get immense learning, immense benefit out of it, which is going to change your career completely to a next level. So with that, I'll close here. Thank you very much. So I see that there are some messages. Let's see. Yeah, I think there is one question here. Sir, how friction doesn't oppose mass M2 to move towards F2? Acha, I didn't check that. So I think you are discussing about the first question. How friction doesn't oppose M2 to move towards F2? No, I didn't understand your question. So first of all, on that particular situation, the way you need to look at it, if friction is not there, if the friction was not there, what would happen? Just M2 moves away, M1 will stay there. That means M1 would want to stay at rest and M2 would move away, and that creates a slipping. So the slipping comes because M1 stays stationary. So now I want to reduce the slip. What should I do? I need to drag M1 along with M2. So on M1, I need to have a friction in the direction of motion. Then according to Newton's third law, if on M1 force is right side, on M2 force has to be left side. That's how you need to look at it. Whenever you want to find the direction of friction, first imagine a situation where friction is not present. Yeah. So when friction is not present, what would happen? Slipping happens. Now friction comes to reduce the friction, slipping, or to completely avoid the slip if it is possible. That's a situation here because it's a static friction. So now M1 stays there, because of that you have the slip. So to avoid slipping, friction has to drag it along. I hope you understand that question. Okay, then another doubt is there. Forces are not equal in magnitude. Do both the blocks come to rest finally? In ground frame, the motion is complicated. In ground frame, it is like they are moving, oscillating and also translating. So it's very complicated. It depends on F1 by M1, F2 by M2. If F1 by M1, F2 by M2 are equal, then maybe, yes, they may come together simultaneously at rest in ground frame. But ground frame, it's very complicated, as I told you. With respect to center of mass, if you observe it, then you see that the net force, including pseudo force, they become equal, and then they oscillate very easily and they come to rest simultaneously. They go in opposite phase. When it goes to the extreme position, this also should go to extreme position. They go in tandem. So they'll have a phase difference of pi. It's a simple harmonic motion that you might have studied about. So in CM frame, it is very easy to analyze, but in ground frame, it is complicated. Yeah, so I think Mr. Kiran has given you an idea. So there are some lecturers available who would like to clear your doubts. Okay. Okay, then I'll leave it here. So all the best for your future. Hope that you make use of this platform very effectively, and then grow faster, because there's a lot of demand for the qualified faculty right now, especially after pandemic. So many opportunities are coming up, and good rises are also there. Now I am running an institute in Hyderabad. Even I am having a shortage of faculty. Right now I required 3 faculty, one for each subject, who can teach up to IIT advanced level. So likewise, there are so many opportunities, you make use of it. Okay, then I'll close here. You can speak to Mr. Kiran regarding all other details, right? Whatever information you require additionally, you can touch it in contact with Kiran, sir. So he will give you all the details. Okay, then I'll close here. See you. Thank you.